All right, this is the start of the videos for week 2. 2A1 is the first one. We're going to be calculating per capita and using proportions for scaling. So first of all, you have to know what per capita means. It means per person usually. We're going to be dividing. So our last shopping trip allowed the group to eat 360 gummy candies for the 12 people included on the trip. Find the number of gummy candies per capita or per person. Do not round. So it was 360 gummies per 12 people. If we divide that, we will get, and it comes out evenly this time, 30 gummies per capita, which for us, remember, means per person. There are 175,000 registered German Shepherds in a country with 13.2 million people. Find the number of registered German Shepherd dogs per capita. Okay, so registered German Shepherd dogs is 175,000. Country is 13.2 million. So we don't want to just put 13.2. We need that times 10 to the 6th for the million. So this is our German Shepherds. This is our people. This time we're going to round to 5 decimal places. So let's go ahead and divide that. 175,000 divided by parentheses. Anytime you divide by scientific notation, put it in parentheses. 13.2 times a 10. Use my exponent button to the 6th. Close my parentheses. Hit enter. And that is 0.013257. It looks like the 57 just repeats after that. We wanted to round to 5 decimal places, so 1, 2, 3, 4, 5 with the 7 after it. That means that 5 would bump up to a 6. So 0.01326 German Shepherd dogs per capita. Now, that seems a very weird answer to give. That's what they wanted us to do, but, like in terms of, that's not even a whole dog. So something you can do, since this is per person, I'm just going to write this over to the side. This is not how they wanted the answer, but just so you have a little frame of reference of things you can do to something like this. If you have, so this is a little extra information. If I have 0.01326 German Shepherds per one person, if you move that decimal one place to the right, that is like multiplying by 10. So 0.1326 German Shepherds per 10 people. Okay, still not a whole dog yet. If I move it one more to the right, that'd be 1.326 German Shepherds per, and we moved it one more place to the right, so that adds another 0. So, even though they wanted the answer rounded to 5 decimals, we followed their directions. It's just, if you were talking to someone in a conversation, you wouldn't say, I have 0.01326 German Shepherds per person. I mean, that's what it is, but it just doesn't make as much sense to someone because they're like, well, whoa, that's not even a dog. So every time you bump it one place to the right, your per person gets multiplied by 10. So essentially it's about 1.3 dogs per person per 100 people. So that, at least gives a little more realistic frame of the discussion. So just be aware of that. This is just extra, wasn't part of the answer, but it is a nice way to scale it to a number that makes sense to us. A town has 33 schools and a population of 102,000. What is the number of schools per capita, so per person? So 33 schools divided by the 102,000 people, because remember per capita for us is per person. So 33 divided by 102,000. That is now that gives me scientific notation. I like this one in our examples because sometimes students don't recognize this. If there's ever an e to a power at the end of your problem, that is in scientific notation. So 3.235294. I'm just writing out to a few places. 0.1176. We're just writing this out a little bit, times 10 to the -4. Our calculator doesn't do the 10, it does the E. So this is not rounded to 5 decimal places because, first of all, they want this in a regular number. If they wanted it in scientific notation to 5 decimal places, it would have said round your answer as a scientific notation number to 5 decimal places. So we need to first convert this to a regular number using the going back to standard form, and then we round it to our 5 decimal places. So -4 is an exponent, means move 4 to the left. So 1, 2, 3, 4, put our zeros in there, and then we're going to round to 5 decimal places. So that'll be 0.0003, and that 2 is in the 5th spot, a 3 behind it, so it's going to stay a 2. So 0.00032 schools per person, which again, or per capita, doesn't make a lot of sense when you talk about that not even being a whole school. It's very, very it's very far away from being a whole school. So if we wanted to talk about this in terms of whole schools, I would have wanted it at 3. And I would have added and ended up multiplying by 10 4 times to get to that movement. We would have said 3 schools per, let's see, that'd be 1 move, 10, 2 moves is 100, 3 moves is 1,000, 4 moves is 10,000. So you could adjust it if you were doing an everyday conversation with someone, but we followed our directions. Example 4, Antonio and Juliet are opening a new business. They decide to send informational packets to relevant businesses in the extended community. They are including 3 things in each packet and creating 400 packets total. If there are 5 people creating the packets for distribution, what is the number of packets per capita? Now, there's extra information in here. We already know the total number of packets. We don't really need to know how much is in a packet because they're just throwing you off with that. Packets, number of packets is 400, and per capita, for people working on it, is 5 people creating. So this would just be 400 divided by 5. That's going to be 80 packets per person or per capita. So each of those 5 people is going to create 80 of the packets. A 3rd grade classroom consists of 24 students and 1 teacher, so 25 total people in the room. 1 student brings in individually packaged candies to share with the class and the teacher. So we do need to include all 25 people to celebrate their birthday. There are 150 pieces of candy for everyone to share. So we're doing a total of 25 people. We have 150 pieces of candy. If everyone receives the same number of candies, find the number of pieces of candy per capita. So 150 divided by 25, this one also comes out even, so we don't have to round, is 6 pieces of candy per capita or per person. At a recent Major League Baseball game, 56,732 hot dogs were served on $1 hot dog night. If there were 41,531 people in attendance, what is the number of hot dogs per capita? Again, they're throwing extra information in this one. We don't need the $1 amount because they didn't ask us about the price in the final question. They just want to know number of hot dogs per people. So 56,732 hot dogs divided by the 41,531 people. And we want to round this to 2 decimal places. So let's look at our calculator. 56,732 divided by 41,531. That is going to be 1.366 is to 3 decimal places. We wanted to go to 2, so 1.37. The 6 will bump up that other 6. So approximately 1.37 hot dogs per person. Okay. This one we already did in the last problem, similar. So I don't know, I guess I just included it here too because it's sort of like a per capita problem, but they asked people per hotel. not per capita. So just be aware that sometimes it's not a per capita problem and you might have to set it up the opposite way. So this is 386,202 people for 298 hotels. We did this one on another page just in section 1B3. This came out to 1,296 because it was 5 point something that rounded up people per hotel. Okay. All right, so using proportions to scale values. This is from those application proportions that we were just doing, but we can now do proportions and look at things. So a lot of times they will have you scale to 100,000 people. That's a very common scale we see a lot of times. So notice this one says Indiana averages 82,650 births each year to a population of 674,360. So sorry, 6,744,5,360. How many births could we contribute to 100,000 people? So we're saying, okay, if we're doing birth over population, birth over population, and we want to know, well, instead of looking at the whole population of Indiana, what if we only want to scale it to 100,000 people? And a lot of times they do that because then that gives you like reference for if a city has a population of around 100,000 people, we would expect around this many births, possibly in that city. So if we look at this, this is 82,650 times the 100,000, which you could do times 10 to the fifth because that is what 100,000 is. So you could do that if you wanted. Divided by the number across from X, which is 6,745,360. And we're rounding to the nearest whole for each direction. So that's 1,225.2. The 0.2 will not bump it up. So it's going to be X is approximately 1,225 births per 100,000 people in Indiana, just to give you a frame of reference of what we just found. Okay. There are 354 ice cream shops in a city that has a population of 752,500. How many ice cream shops should there be just if we narrowed that down to 100,000 people? So again, scaling. So 354, we're gonna do ice cream on top, population on bottom, over 752,500 equals how many people over 100,000? Cross multiply, we need to multiply the 354 times the 100,000. And then divide that by the number across from X, which is the 752,500. And round to the nearest, well, they didn't tell us to round to the nearest whole, but I am going to since they, I think it was just left out and this was in wholes. So for 100,000 people, we should expect roughly 47, that is not a good 4, ice cream shops. Shops per 100,000 people. Okay, so just some review of converting numbers between standard form and scientific and just working with those words like billion, million, and trillion. So the first thing I'm going to do is write out what each of these would look like. So 13.2 million is 13,200,000. Okay, so because the point is going to be after the million block. So it's going to be in that 100,000 place. 320 million is 320. And then we have 6 places. Since there was no decimal, you get to add all 6 as zeros. Be careful with this one. 0.67 trillion is not even a full trillion because it doesn't even have a whole. So this is actually 670 billion because anytime you have your numbers, think about where your trillion is. 1 trillion is followed by a comma, and then the next 3 digits are 100 billion, 10 billion, and 1 billion. So if this is where a trillion is, and that's our decimal, that means it's 6, 7 right after that. So 670 and that's in the billion group. Okay. So those are always tricky when it's not even a whole amount. So this is going to be 670. Those are all in the billions. Then we have our millions, our thousands, and our ones, essentially hundreds and ones. So you can check that one when we see in scientific notation if we're correct on that. And then this one does have a whole amount. So 52 is in the trillions, 86 is in those first two spots of the billions, then millions, then thousands, then remember our ones group. Okay. Now, if we take these and we ignore these numbers right here, let's just write these with the times 10 to the 6, 9, and 12 that we see for million, billion, and trillion. So this would have been 6.8 times 10 to the 9th, because it's a billion. 13.2 times 10 to the 6th, because it's a million. 320 times 10 to the 6th. 0.67 times 10 to the 12th, because it's a trillion. And 52.86 times 10 to the 12th, because it's also a trillion. Now we want to put them in correct scientific notation. Okay, so this one's already good. So they said don't do it if we don't need to, but it's already there, so just might as well write it. This one needs an adjustment 1 to the left. So that's going to be 1.32. So that means we add 1 to our power because we moved to the left. This one's going to need an adjustment 2 to the left. So that's going to be 3.20 times 10 to the add 2 to our exponent will be 8. This one would need an adjustment to the right. So that's going to be 6.7 times 10 to the, we have to lose 1. Remember when we move to the right, Lars. Right means subtract 1 from our power. So see, now you're not even in the trillions. See, that's where we end up. Oh, it's actually in the billions. And then this one needs an adjustment 1 to the left. So 5.286 and add 1 to the power. So that's going to be 13, which makes sense because it is in the trillions still, but it's in the tens place of the trillions. It's because it has 2 digits in front of the decimal. So that's just some more practice with using your scientific notation and adjusting. So let's look at example 3. It says in 2021, there are 649,000 licensed Starbucks locations in the US. The population in the US in 2021 was 332.9 million. What was the rate of Starbucks locations per 100,000? Okay. So I'm going to be using times 10 to the 6 when I write my ratio here. So I'm going to use n for the unknown. So we have our Starbucks and our population. We knew that we had 6,497 Starbucks out of 332.9 times 10 to the 6 people. I don't know how many Starbucks that is per every 100,000 people. And again, I'm actually going to write this time 100,000 is 10 to the 5th. Because remember, we learned when we have a number with a 1 and a bunch of zeros, it is 10 to the number of zeros after our 1. So that's 10 to the 5th. So writing it like this will make this a little bit easier to do the problem. So this will be 6,497 times 10 to the 5th. Equals 332.9 times 10 to the 6th, n. Divide both sides by 332.9 times 10 to the 6th. 332.9 times 10 to the 6th. We're going to go type that in on our calculator. 6,497 times 10 to the 5th. And then divide by, always open a parentheses for the bottom one, 332.9 times 10 to the 6th. And notice that gives me 1.95. I'm going to round to 2 decimal places. They didn't tell us. So that would be roughly 1.95 Starbucks per 100,000 people. Okay, so almost 2 Starbucks per 100,000 people. So let's look at another one. New York State has 215 state parks. The population in New York State is 19.45 million. How many state parks per 100,000 people are there? And we're going to round to the nearest hundredth. So again, 2 decimal places. So 215 state parks over population. That's when we have 19.45 times 10 to the 6th. We want to know how many parks would that be for 100,000 people. Again, I'm using 10 to the 5th. If you want to write out 100,000, feel free. Either way is fine. So 10 to the 5th. And then we're going to divide that by the number across from n. So remember, always do parentheses because you're dividing by 2 multiplications essentially. So 19.45 times 10 to the exponent of 6. And that is 1.11 because you'd have a 0 followed by a 5. So to 2 decimal places, the hundredths, that'll be 1.11. So about 1.11 state parks per 100,000 people. Okay. That doesn't look very good. Let me see if I can rewrite that a little better in there. And then the last one for 2A1 is there are 249 motor vehicle fatalities in Connecticut in 2019. Population in Connecticut in 2019 was roughly 3.565 million. How many motor vehicle fatalities were there per 100,000 people? So again, we're doing the same thing. We're just doing a different scenario. So motor vehicle fatalities over population. And remember, I'm using 10 to the 5th because I know that that's 100,000. If I was doing 10,000 people, I'd be doing 10 to the 4th. So be aware of that. It's not always 10 to the 5th unless you're always doing 100,000. If you're doing a million per 1,000,000 people, you'd have 10 to the 6th. If you're doing 10,000 people, you'd have 10 to the 4th. So if you want to use that shortcut for scientific notation, that's fine. Just make sure you count the appropriate number of zeros that they told you. And that's only when we're going to those nice even numbers where it's a 1 followed by a bunch of zeros. So 249 times 10 to the 5th divided by parentheses 3.565 times 10 to the 6th for the million. And this is going to be 6.98 rounded to the nearest hundredth. So about 6.98 motor vehicle fatalities per 100,000 people. Okay. All right. That is the end of 2A1.